So now we'll go over some practical exercises on MATLAB, on MATLAB. The first one is design, so you can search for it online. Design multi-loop control system. That's the exercise. Design multi-loop control system. We'll go over it. As you see, it's 2 degrees of freedom. You have compensation feedback in here, and we'll see how to go over it. So yeah, I recommend you to go over and look to them. In many applications, a single loop control system is not feasible due to your plant design or design requirements. So single loop may be not feasible. So if you have a design with an inner and outer loop, you can use Control System Designer to design compensator for both loops. So we'll use Control System Designer app. So, and the way to go over it is basically as we explained in the theory in our session 3. And in this session 3, okay, more advanced architect session 3. So it's basically we design for the inner loop first by isolating the inner loop from the rest of the control system. Once the inner loop is satisfactorily tuned, then we tune the outer loop to achieve your desired closed loop response. So basically that's it. So we tune for the inner loop first, then the outer loop. So let's take this example. You have DC motor, you have input, as we know the DC motor how it is, VA as input voltage to it, and the output is the angular velocity 1 over S, so you can have the angular position. Okay, so that's the outer loop and this is the inner loop. Okay, so this is the inner loop and this is the outer loop. So in the outer loop you have C1 as a controller, and in the inner loop you have C2 as controller. It's compensator feedback compensator. Okay, so that's the system how it looks like. Of course here is minus plus minus, so negative feedback. Okay, so that's how my system looks like. All right, so these are my parameter. They are giving you the parameter, the resistance, inductance, K, electromotor, motor is constant, etc. The back electromotor is constant. All of the constant, all of the parameter, and then you define it as state space model. So if you remember the state space model from DSM, dynamic system modeling course, we represent the system by ABCD. We'll get refreshment about them, about modeling using state space representation in our first chapter later, our first chapter in state space control design. But for now, based on your DSM knowledge, dynamic system modeling knowledge, well, the matrix A, B, C, D, and D are given. So for now, don't worry about. Then use SS, A, B, C, D to get the system. Well, so you don't need to worry a lot about this is I'm telling you. So maybe it is here where I can find this is. Okay, not a problem, not here, so maybe here. So assuming these are my parameter, ABC sys. So when you say sys for the DC motor, state space SSABCD in MATLAB, you write this comment given to them the A, B, and C and D matrices, then you will get the transfer function. So assuming now I'm giving you the transfer function, so don't worry much about this is the transfer function, which is your system actually. So this is your system. All right. You can simply say TF of it to get the transfer function. So that's your system. Or you can say I want the zero pole gain representation. So you can have it as zero pole and gain. So you have a gain of 1.5 and you have 2 poles. So you know the system is stable. It's a DC motor, of course, it's a stable system. Alright, so nothing than a transfer function, okay? But it's another representation, it's state space representation. And this is how, if you want to know from where it came ABCD, we refresh your memory about later in our state space representation design. But basically, they came from the equation of motion, from the differential equation, electrical and mechanical, of your motor. So you get them this way, and this is x dot. So x is, if you wish, this matrix is this vector x component of it, I and y, w. So this is x dot, derivative with respect to time equal a. This is the matrix x plus this is matrix b. So it is a vector actually, this matrix, and this is u. Okay, u is also could be a vector. In this case, it's a scalar, only the applied voltage on the armature. Okay, and the state are x. X is the state, which is represented by two state, current and omega, the angular velocity. Y the output. So this is y usually is a vector, but here is a scalar, only have one output. So the input is y, is also u. In general, it's multi-input, could be multi-output. In our particular case, the input is only one input, v applied. So if you wish, u equal v applied, and y is small y, so because it's only scalar, and more precisely, if you look at it, equal to your omega. Okay, your, and this state representation equal to the omega. So the input is the applied voltage, and the output is the angular velocity. And in here you have the state, which is I, and W also, which is your output. This one of the state is your output. Okay, so this is Cx plus du. So this is a representation of the system A, where A, B, C, and D equal to that. A equal to this, you have the parameter, so you can have A, B, C, and C is 0, 1, and D is 0. Okay, so that's how they get it. So then again, your input is, remember, your input is V applied, and your output is omega. Okay, your input is V applied, and your output is omega. Alright, so that's A, B, C, D, A, B, C, D, and then you get it. Okay, from here, actually, you can go into this link if you wish, linear time and variant models. We talk about different type of models, but now we care about this example, DC motor. And you have, by the way, the modeling of it in here. They are modeling it for you, it's not that hard. Okay, so now we have it. Now we care about the model itself. The model is state space representation. I can convert it to, if I wish, to a, a transform function. Okay. So then, what's my design requirement and of design objectives? The design objective is to minimize the closed loop step response settling time by maintaining an inner loop phase margin of at least 65 degrees with maximum bandwidth. Okay, this is reflected by three design requirements. Minimize the closed loop step response settling time. Minimal closed loop step response settling time. Second, while maintaining an inner loop phase margin of at least 65 degrees. Inner loop phase margin of at least 65 degrees with maximum bandwidth. Maximum inner loop bandwidth. Well, they didn't precise what is maximum exactly, what is minimum for the closed loop step response, but those are the design requirements for me. So, but for the inner loop phase margin, they mention it, at least 65 degrees. Okay, so those are my design requirements. So let's follow the tutorial step by step. Match system to control architect. So now I can go and open my control system or the CISO tool if I wish, which is the control system designer. I just open it as empty now. That's the one we have. They are telling you, because I need to follow the tutorial, match system to control architect. So that's my system. Follow which architect? Well, the most closed architect is this one. So that's the architect that I want to use. What about H? H all by default now are 1. So now, what about G? My plant. My plant has an input U and an output Y. Well, output should be theta then. Then, whatever you have here, let me copy paste it to create let's create another MATLAB, another. Okay. So in here, I'll create an M file. And, well, I name it maybe, I give it design multi-loop control system. I'll name it this way. Of course, MATLAB doesn't accept like this. What should I have inside it? My parameter. This is my system. And, well, we will make the system this way to be very close to the one we have here. So then my plant, this is my plant, and this will be my C2. Why I did this? Because you look to the system you have, the feedback come to omega 2 from here. But to match this, the output should go like this, and from here you have C2. You see, so it's not the same. So C2 is connected to here, but in our architect, C2 is connected to the output here with H equal 1. So then how to do? I need to like the output to be connected to C2. To make this, simply when I multiply by 1 over S, my model which I have here, which I called it my plant, which I call it sys under DC. Alright, so this sys under DC, this is the sys under DC VA omega. If I multiply it by 1 over S, I get theta. Alright, so here is theta. Then if I multiply by S, so here I divide by S. If I remultiply by S, I get omega. Of course, I have omega, I divide by S, I get theta. I multiply again by S, I return, I get omega. then omega C2, right? Because you care about in your system actually omega that go to C2. That's my system that I'm modeling. Omega goes C2. So my feedback compensator is to control the speed, and C1 is to control the position. Get so that's it. So then to make it this way and to make it match this architect, so that's what I use. I multiply this by 1 over S, and I multiply C2 by S and consider it as C2. So my C2 is actually C2 times S. Alright. So knowing that, then I can say my plant, define my plant as this under this, which is this one, times 1 over S. That's 1 over S. And I create a CDIF initially, which is only S. Then I design the control. So let me have them both in my code. Alright. Alright. So then if I run it, I simply run it just to make my parameter defined. So here it looks like I'm defining all my parameter, but because I don't have comma here, so that's why I have all of them stated, but otherwise you don't need to. But all are defined, as you can see from here. You have KB, plant, R, etc. So now let's keep following the tutorial. What did they say? So it takes this architect and define C1 and C2, C2 as S and G as the plant, G as the plant, and C2 as CDEF, which is S. Then I define G as my plant, and I define C2 as CDEF. I think that's how I wrote them. C capital letter def and plant. Alright, so now we look in this architect. So it looks like it opens for us a lot of things. Well, let's see the tutorial. Continue the tutorial. So which is more than what we usually have in this architect. Now it opens for me more things. Why? So when we look now, we'll see that it opens for you the photos. So if you want the figures for the inner loop and for the outer loop. Let's continue the tutorial. Okay, so our goal is to design first the inner loop and later the outer loop, as we learned in theory. But here is a practical wise, if you wish. So, and we learn how to do using the CISO tool or the control system designer tool. Okay, the app updates the control architect and imports the specified models for the motor plant and the inner loop control. So you can go over them and read what did they open for us actually. Okay, board editor for C1, board editor for CDIF, which is C2. Okay, they call them CDIF and C1, which is because it's a default name. So the for C1 and C2 body diagram for C1 and C2, and root locus for C1 and C2, and the step response for output over input from R to Y, reference to Y. Okay, let's continue the tutorial. They tell us close C1 and C2 plots. Close. C1 and C2, both editor for C1 and root loop is for C2. Body editor for C1 and root loop is for C2. Okay. And now, since the inner loop is tuned first, configure the plots view, the plots to view just the inner loop body editor plot. So just to view, so I have three function. I want just to view the body plot of the inner loop. Okay, that's the C2. C2, remember, is the inner loop. So now I want only to view this. I click on it, single view, so I'm able only to see the body plot of the inner loop. Remember the design requirement. It's good to remember the design requirement for the inner loop. Inner loop, it has a phase margin of at least 65 and the maximum possible bandwidth. Why the maximum? Because it should be faster, at least should be faster than the outer loop. Inner loop should be faster than the outer loop. So just why if I increase the bandwidth, make it faster, so then yeah, that's the required. And phase margin of at least 65 degrees. So now how to isolate the inner loop in your design? Isolate the inner loop. So then just keep the inner loop and disconnect the outer loop. So how to disconnect this? To isolate the inner loop from the rest of the control architect, add a loop opening to the open loop response of the inner loop. Let's see how to add to the loop. Add a loop opening to the open loop response of the inner loop. Let's see what to do. In data browser, right click on and select open selection. So here usually in the response view, so you right click wherever here, you right click and you click on the open selection. You can also delete something from the responses, so you don't have open selection now. Okay, also you can plot step, body, impulse, Nyquist, anything you want. So here is your responses. Actually you have a lot of response. For example, loop transfer C1, loop transfer CDEF. If I double click on it, so it give me the loop transfer C1, which has UC1. That's the loop transfer U. So it give you this response. So you can click OK, for example, and it will be presented. Okay. Input output transfer, for example, between dy to y, or input output transfer between r to y, which is r to y, which we can see it. So now this is actually, if I double click on it, r to y, from r to y, which is already selected. But for you, they told you click and right click open selection. But click where they right click on the loop transfer C2 and select open selection. Loop transfer C2, this one. So you can right click and open selection this way, or you double click on it. That's what you get. So loop transfer CDEF. Follow the tutorial. To add a loop opening, by default is putting for you UC2. Here to add a loop opening at the output of outer loop compensator C1 and the open loop transfer function dialog box. Here click add loop opening location to list, then select UC1. So basically what we did here, that's the loop, and here is the opening. Then add loop opening location. From where you want to open the loop, you open the loop from here. It is very important. Why I want to open the loop from here? Because that's the inner loop and that's the outer loop. It joins, the outer loop joins the inner loop at this point, so you open from here. So then by default you have your UC2, because UC2 is here. So here is the open loop, your open loop for the inner loop. It takes from U up to UC2, that's the open loop. So that's why you have UC2 by default. But where to open the loop? Open loop response with the following loops open. Here is the loops that you want to open. So you take it out. Well, let me to make it easy to clarify it a bit more. Let me think about this one. For example, assuming I have same scenario, here is my inner loop, and here is my outer loop. So if I have the same scenario, I want to design for the inner loop first. Then of course later on for the outer loop. The loop opening is here. The open loop for transfer function that I care about for the inner loop. So if I consider the pink loop alone, is here, which is y2 at the end is y2. But from where I need to open the outer loop? Okay, from where you want to open the outer loop? Is it from U1 or from here, or from Y1? From Y1 or from U1? Do I open it from here or no from here? So when you want in here, when you do this and you want to specify, do you just hide them? Do you open it from UC1 or from YM, according to the analogy that I show it to you here? Right? Do you open it from the output of the controller or the output of the main output, Y1 or U1? So same analogy, YM or UC1. Well, let's say you want to open it from YM. Then, assuming here also you want to open it from YM. So you still have, so basically the loop is opened. So you still have like this loop as this. It will be added to here. And that's the inner loop anyway. That's the inner loop. Here, that's the inner loop. So the first input gets from here. Here is the inner loop. The first input gets from here. But your controller is here. Here the difference is your controller is here. If you open the loop from here, in this scenario is wrong. Because, simply speaking, let me start by here first. If you open the loop here, if you open the loop from here or there, for both scenarios the loop will be open, and then it's open. So you can select U1 or Y1 to open the loop. At the end you are cutting. So you take the scissor and you cut from here or you cut from here. So then this is not affecting your inner loop. So then if you tell me I will cut from here, I tell you it's right, so you are open the loop. Because if you cut from here, so whatever here they come and they are reach here, but they cannot continue. So it's not affected by. So it's right. And if you cut here, it's also right. It's even better. It's even better if you cut here. So you don't need to go one step forward then. So just you cut from here. Okay. So from here, from your output. So once you cut from here, then the loop is open. So you don't need to go step. Why I want to do more calculation for nothing. So better to cut from here. But both are right, and this doesn't affect. At the end, your loop is opening now. So then you focus on the inner loop. But in this scenario, you cannot cut from here. That's the point I want to point it out to you. You cannot cut from here, YM, because if you cut from YM, you are opening the inner loop. See, you are opening in this case the inner loop as well with the outer loop, because the same point here and here. So then you cannot cut from here, so you cut from here. So that's why I chose UC1 to open the loop to consider. So then I isolate my inner loop. That's how to isolate your inner loop. You cut from UC1. Good. So then you go and you add UC1 as they did in the tutorial. Okay. Let's follow the tutorial. See what's next. Then this opening removes the effect of the outer control loop on the open loop transfer function of the inner loop. The board editor response plot updates the reflect to reflect the new open loop transfer function. Let's see. CDEF. Alright. It looks like your plant is still empty. Let me go and check my architect. This is my fault. I make it here, so actually this is C2. Let me call it C2, and it was G, I believe. Then I put a plant here. So this is the plant should be putting here, and CDEF is here. Sorry guys. So the CDEF, okay. The plant take it as ABCD. CDEF as S. Well, I prefer to re-edit the session again. Okay, so I will close it quickly. Alright, and open it. So now we don't need to explain anything because I will select my architect and I take CDEF for C2 and the plant for alright, and I'll use the option 0 pole gain as we always do. Then they said for us, just to remember in the tutorial, keep C1, C2 body plot and the input out. So body plot for C2 and root locus for C1. So keep only body plot for C2 and root locus only for C1. Alright, so then because we're interested on this now, so then single view. Let's do single view. So now I'm interested on this, and you click on it or double click and use, as we explained, UC1, and then it will get affected by. So then this is change this how. Good. Tune inner loop. We need to tune the inner loop to increase the bandwidth of the inner loop, increase the gain of compensator C2 in the body plot, drag OK until you achieve a phase margin of 65. Let's go. So they said it's a gain of 107. Let's see. I drag it and looking to C2 a phase margin of, so keep going, phase margin of 128. So they want phase margin of how much? Okay, infinity now. Okay, so it's decreased, phase margin decreased. I keep decrease it until it reaches 65, if I remember in the tutorial. 65 degree. Keep increase it until you reach 65 degree. Okay, so the 68. Well, they said 107, so let's go, so we can keep tuning, but easily 107, and it's supposed to give you the phase margin you need, 65 degree. Okay. And this has a frequency of 10.4 radian per second. 10.4 radian per second. That's the fastest I can achieve. That's the fastest I have actually frequency. The fastest, the maximum bandwidth for the inner loop. Now, if I want to design for the outer loop, I should be at least 10 times a decade below it to be slower than 10 radian per second. Now we will tune the outer loop. With the inner loop tuned, now we tune the outer loop to reduce the closed loop settling time. Well, let's look at the settling time. Now I'm using two view. Using here, he decided to use root locus. So now maybe if I keep control on both, well, let's see view and left right view, and I have root locus. So now if you look to the settling time as a characteristic, it is 500 seconds almost, right? Then we can play on the gain. You can play on the gain as the gain increase. Those are my poles until achieve a small settling time. Like here, these are my gain now for C1. So let's look for C1. It's a gain equal 1. I have third order system. Root locus, the closed loop. This is the root locus for loop transfer C1. So now we are taking, of course, if you need feedback, if you remember, we are taking that system. Of course, this is one. This is your plant, which is maybe second order system, but now we are represented by ABCD and multiply it by 1 over S. Alright, remember, multiply by 1 over S. So then in our design, we take the open loop. So we take from here to here, like like here. If I have dynamic, I don't have dynamic, so it's Y over E. Alright, that's the open loop dynamic. Open loop transfer function, Y over E. This is the transfer function, open loop transfer function. Alright. Open loop transfer function, if you are not sure, click on it. So we find it's opening at UC1. Well, what's the difference? So like if I take this, the open loop UC2, we saw in a while. We said it's specifying the open loop response at the following location. So specified at UC2. Alright, so I can then, my body diagram was taking the open loop from, it's like the transfer function will be GHC2 because my response counted from UC2, but for the inner loop. Okay, so then I specified it and I open it from here. I explained why in a while. But for this, by default it is UC1. So if it's UC1, it's from where I'm counting my root locus for loop transfer. The loop transfer C1 is UC1 and it's the outer loop. So UC1 to E. So then it is only the controller itself. UC1 to E. Okay. Previously for C2 was UC2 to U because that's the inner loop. Then GHC2. Here is only C1 and take. Well, can I take YM? Yes, you can take. You can change it. Put YM. In the tutorial, they kept it UC1. You can change. You put YM. Doesn't matter. What it will change? It will change the response of the root locks. So now, let's keep it as it is. Then later I'll show it to you if I take YM instead of UC1. If you are taking UC1, means you are computing. You are considering the root locus for C1 only. But the system itself, the app knows that this is part of the outer loop. Okay, C1 is for the outer loop according to the architect, our architect. But if I take YM, so then I will get the root locus for the open loop transfer, for the open loop transfer function of the outer loop, which is C1 GH. If I take YM, maybe you are more familiar to take YM, but let's keep UC1. This doesn't change anything. Later I'll show to you how if I'm putting YM that nothing will change. So I need to close it just. Okay, then changing the gain make the system faster. Let me click on C1. Okay, make more faster. Like here in the tutorial, they get 600. Okay, so 600 it give you a settling time of 0785, 078. All right, so exactly same responses, 078, so around 08, and a neural loop phase margin of 65 degrees. So then I'm satisfying my design requirement, and it's the end of this tutorial. So let me show to you now what if I take C1. Now add YM, right? And then let me delete this and keep only YM. Look at the root locus. When I say okay now, root locus is changed because it's computing the loop transfer starting from ending at YM. So computing the open loop transfer function of the outer loop, but the response itself doesn't change, and your gain is still the gain that you had. Nothing changed, just the shape of the root locus taking in your figure is different. Okay, yeah, that's it for this tutorial.